Hi folks, we're going to take a look at number 7D from page 126. So they ask us to find the vector equation of the plane that contains these parallel lines given here. Now, you can tell pretty easily that these are parallel lines because if you look at the ratios of the components, 4 over -6, 2 over -3, -4 over 6, you realize that they all give you -2/3. Okay, so these are parallel vectors, hence parallel lines. Okay. So in order to find the vector equation of a plane, we need a point, which we have 2 points here since both of these lines are on the plane, and we need 2 direction vectors. Now it might be tempting to take the direction vectors from each of the lines, but here remember that these lines are parallel, hence their direction vectors are parallel. And one of the conditions on direction vectors for a plane is that they cannot be parallel to each other. Okay, so I could definitely take one of these as a direction vector, but we're going to have to create another direction vector. But if you look here, if I take a point on one line, say 0, 1, 3, and I connect it to a point on the other line, say -4, 5, -4, I can create a vector which is not parallel to either of these lines. Now, of course, one thing we really should be checking is, that these lines are not coincident. So they don't specify that. So I suppose we really should check that that's the case, because if these actually represent the same lines, then we can't find a unique plane that passes through them. So I think they're expecting us to assume it, but let's actually check it out. Okay, so let me see whether the point 0, 1, 3 is on that line there. So I need the x component 0 here to be able to be written as -4 plus 4s. So I just took the x component from that equation. So that gives me 4 equals 4s, so s would have to be equal to 1. Now let's see if that value of s equals 1 produces a y value of 1. So here we'll take the y value is 5 plus 2s. Okay, but here now we know that s has to be equal to 1. So 5 plus 2 is 7. That is not equal to the y value of this point. Hence, these two lines must be distinct. So we can sort of continue on with our procedure here. So what we were thinking of using will work. Okay, so let's call this vector A here. Okay, that's used for one of our direction vectors. So here's vector A, and I'll just take the vector joining these 2 points. So here we've got, I'll try to get rid of some of these negatives. So I'll go this way. 0 minus -4 is 4. 1 minus 5 is -4. And then 3 minus -4. So 3 plus 4 is 7. Okay, and now I need to choose a second direction vector. Now, I could use either of these, but I actually noticed that both of these are not in reduced form. So I'm going to take a third vector which is parallel to these here. Okay, so this is something you should try to get used to doing if at all possible. So if I take this vector here and I divide each component by 2, so in other words I'm multiplying the vector by 1/2, I just end up with 2, 1, -2. Okay, so if 4, 2, -4 is on the plane, means 2, 1, -2 will also be on the plane. So this will be a simpler vector to use as a direction vector. So just be sure here this is the number 1 and not -1. Okay, now that I have 2 direction vectors, I can pick one of the points. This one here seems easier, and they're looking for the vector equation here. So I've got 0, 1, 3 plus s times 4, -4, 7 plus t times 2, 1, -2. Okay, and if I did want to write this in parametric form, we might as well do that here. So 0, well, we'll write that down. So 4s plus 2t, and the y component will be 1 minus 4s plus t, and then the z component will be 3 plus 7s minus 2t. Okay, so there you have it. Okay, again, anytime you need to find the vector parametric equation of a plane, keep in mind what is it you need. You need a point, and you need 2 non-zero, non-parallel vectors. Okay, that's it for now.